Right, good morning. So welcome to our first session in anger, as it were, to get into the details. It's always slightly a nightmare when you have to introduce people and they have names that are difficult to pronounce. I guess we're just going to have to call this guy David Lou Bang Bang. But maybe he'll go by David. So David's going to talk about URDF. Please welcome David.
Good morning. It's a pleasure to be talking to all of you here at the inaugural ROSCon. My name is David Liu. I'm a PhD student at Washington University working on expressive motion for improving human-robot interaction, and not, as it turns out, URDF. URDF is just something that I've spent a lot of time working with. I didn't actually develop the standards, so take everything I say with a slight grain of salt. Yes, we're talking about URDF today. Mostly URDF, not as much about you, I'm sorry. And URDF is the Unified Robot Description Format. And what that is it's a file format that allows you to go from a physical specification for your robot, like we have on the left. This is WashU's B21R, named Lewis. And then you go from that to a XML representation of your robot. And then it can go into a number of different ROS programs and nodes, such as RViz, as you see all the way on the right there. Throughout this talk, there will be little blue boxes on the bottom that will reference wiki pages where you can find more information. Everything that I don't talk about in this talk related to URDF can be found on the wiki page in the specification there. And so when we get down to it, the general outline is I'm going to start with the overall XML specification, all the elements that you can put into URDF, and then where those elements are used throughout ROS. And then I'm going to also talk about the tools that you can use to examine and modify your URDF files. And then I'm going to end with some of the limitations of URDF, things that you can't model, or at least you can't model without some small amount of black magic. So when we get down to it, URDF is XML, and it's made up of links and joints. So here we have at the top our XML specification. The overall wrapper tag is called robot, oddly enough. And then inside we have links and joints. So here we have two links, link to the past and link hogthrob. And they are connected with a joint expenditure. And with that, we connect the joint. We connect the two links with that joint, with them having a parent and child relationship. And with that, you can specify the topology of your robot. And so figure out what is connected to what. So the head bone's connected to the neck bone's connected to the shoulder bone's connected to the left arm, back, and right arm. And through this, you can create a tree structure. Every node, or every link has exactly one parent. A node can have multiple children, and what this means is we get this tree structure where there is a root node that is the common ancestor of all the different links in your model. And so on the left here, you can see the XML representation for this model. First, we start off by specifying all of our links and their names, and then the joints that connect them. Important to note here that the order for these doesn't actually matter. You can put them in any order, and they'll all be linked together in the end. Let's see. And so if we take a look at the example I have of Lewis, our robot, we can divide him up into 5 parts. We have the base and the body, which can rotate separately, and then 3 pieces for the pan-tilt unit on the top. And so again, we have the links that I specify up here, and then I have all of the joints that connect them in the order, and so the base is the most common ancestor. So that specifies the topology of our robot, but we would also like to be able to specify the geometry of the robot. And in ROS, all the geometry is represented with coordinate frames and TF, and TF stands for transforms. To find out more about transforms, stay tuned tomorrow at 11. Tully will be talking about understanding TF. But just as a quick overview, in ROS we can specify any number of different coordinate frames and then translate any data that we have into any of those coordinate frames relative to each other. And so the difference between two coordinate frames is called a transform, and it consists of a parent frame and a child frame, again giving us a structure much like we find in URDF. And then the difference is marked by the translation and rotation. The translation is specified XYZ in meters, and the rotation in TF is specified by a quaternion, and fortunately for all those people who, like me, haven't quite been able to wrap their head around quaternions, in URDF it's specified as roll, pitch, and yaw in radians. Just a quick note on convention. In all the visualizations of these reference frames, the x-axis is marked in red, and rotations about that axis are roll. Y-axis is green, rotations about that are called pitch, and then rotations about the z-axis are yaw, marked in blue. And that's typically the order that you'll see things in: X, Y, Z, RGB, roll, pitch, yaw. So if we actually want to put this into our URDF files, we do so with the origin tag. And so on the top left, we have the default with no difference between reference frames, and you can do it one of three different ways. You can do it with no tag, and then that just defaults to no difference. You can specify an empty origin tag, or you can specify the XYZ and roll, pitch, and yaw to be 0. Then top right, you can see an offset just in ½ a meter in the X direction. Then in the bottom left, we're adding another dimension, adding a offset in the Y direction. And then in the bottom right, I'm adding a 90-degree turn around the Z axis specified in the yaw there. And if we actually apply this to our robot, all the links are specified at the top. And then I want to specify that the body link is 0.4 meters above the base link. So I just do that with the origin tag that you can see there. And then I want to specify that the PTU base is about 1 meter above that. And I do that in the reference frame of the body. So I do it in the reference frame of the parent link and and that creates the reference frame for the child link. And so you can see that I've added the origin tag there for the XYZ offset to the PTU base. And then finally, we can do that again to specify that the middle part of the PTU is another 55 millimeters above that with the bottom origin tag that you see there. And this is all the info you need to do some fairly interesting things, such as get the transforms for your robot. And that will give you a visualization like the one you see on the right there with the different reference frames. But the logical question is, how do you get from the XML to the actual transforms? So the first thing that you do is you load the URDF into the parameter server. And so the parameter server, it was mentioned before as one of these core services that is offered. And if you put this line into your launch file, what you do, it will set the parameter named robot description to the contents of the text files. And this is using a common macro to help find the package. So all of the URDF in this talk are in a package called ROSCon URDF, and there'll be a link to that repository at the end. And so this will load it into the parameter server. The next step is to run the robot state publisher. And what this does is it takes in joint state messages, and for each one of those, it will output a set of transforms. And you can find more info on this at the wiki page. It's important to note here, though, that the robot state publisher will not output the transforms unless you provide it with joint state messages. The joint state messages can be provided by the driver that is running the actual hardware of your robot, or if you just want to visualize what your model looks like, you can use the joint state publisher, which is a node that I wrote a couple of years ago in order to visualize these URDF files. And so what that'll do is it'll just publish the default joint state messages. And so you might be asking what is actually in these joint state messages. And right now it doesn't make sense because all of the joints that we've specified so far have been fixed, meaning they don't move. And so what the joint state publisher will actually do is just publish empty joint state messages in order to get the robot state publisher to publish transforms. But most robots actually move. So how do we do that? We can specify the joint types to be one of several different types. So we already explored the fixed joint, which you can see all the way on the left. Next, we have continuous joints. Those can rotate about an axis like a wheel infinitely in either direction. So first, you can see the rotating about the x-axis and then rotating about the y-axis. You can also have revolute joints, which are like continuous joints in that they rotate around an axis, but they have a specified upper and lower bound, so they can't rotate all the way around. Finally, you have the prismatic joints, which translate as opposed to rotate, and they move along an axis that you can specify. So you can see that all the way on the right. There's two other types of joints. I haven't actually seen them used ever, but just so you know that they're in the specification, you have a planar joint, which is like a mouse can move within a plane. And then you also have a floating joint, which does not specify or allows you to have all 6 degrees of freedom free. And so if we were to actually put that into our model again, the relationship between the base and the body, that can rotate fully around forever. So we specify as a continuous joint, and we specify the axis to be the z-axis with that vector there. The connection between the body and the base is fixed. They don't move relative to each other. So we leave that one as it is. Then we have the pan part of the pan tilt unit. That has it can go pi radians backwards and pi radians the other way. It cannot go all the way around, so we specify that to be a revolute joint, and with its bounds there. And it also goes around the z-axis. And then finally, the pan joint at the the tilt joint at the very top can go 0.54 radians up and 0.82 radians down. And in order to get it so that the positive direction is up and the negative direction is down, we set the axis to the vector 0, -1, 0. And so this allows us to specify all of the geometry of this model. Now what we can do is we can actually specify in the joint state message the angles of these joints. And you can, again, do it either with your driver, or if you're just wanting to test things out again, you can use the joint state publisher again with the use GUI parameter set to true. It'll pop up a window, and then you can set the joint angles by hand. And then this will publish to TF. Just another functionality of joint state publisher, you can also use it to combine joint state messages using the source list parameter. So on our robot, the pan tilt unit is controlled by a separate node than the base, and so we publish those two joint states separately, and then they're combined in the joint state publisher to publish one joint state message, which is how the robot state publisher actually wants that information. And so you might be asking, how does the robot state publisher actually do this? What it does is it takes in the joint states and calculates the forward kinematics using the kinematics and dynamics library from ROSCon, and then publishes the relative transforms. Also using this library, you can use a service called to get the inverse kinematics. So given a transform, what are the joint angles that will get you to that transform? And so you can go both ways on this. You can the easiest way to set this up using electric or more modern versions is to use the ARM navigation wizard, which will set up the kinematic chains and all of the code that you need to do that. And so I'll pause here for a second and see if there are any questions, or shall we just forge onward? All right. So this allows us to specify a full kinematic model of our robot. But there are other things that we would like to do with the URDF, specifically model what it looks like. And so this allows us to expand the link tag that we were previously just specifying with a name. And so we can specify the visual tag, and two tags that go in there are geometry and material. So with things like geometry, we can specify primitive 3D shapes like a sphere with a radius of 0.5, as you can see here. And then we can also specify materials, what we want the shape to be look like. Here we're specifying a color named red that it uses the RGBA values 1001. Similarly, we can also make a cylinder like you see on the bottom. And then since we already defined the red material up above, we can just refer to it by its name as you see on the bottom there. There's one other primitive shape that you can use, and it's a box specified with a XYZ size. And then you can also specify the material to be a certain texture specified here with the package protocol and using the logo for ROSCon as the texture. And so you can see it pasted on there. However, most robots aren't composed of just cylinders, boxes, and spheres. So we also allow you to specify a mesh, which you can create in any number of different programs, SketchUp, Blender, or whatever your choice is. Here I'm using the shoulder pan link from the PR2, and you can see it visualized there on the right. You might also notice that I don't specify a material for this one. And that's because this is actually in the Collada format, which is an XML format all its own that contains a lot of different information about how it is to be drawn and rendered. And so you can see this is what the there's image data associated with it. This is what the coloring and normals look like for that. So there's one other important tag in the visual tag, and that is the origin. So we already specified the origin in the joint tag. Why do we need to specify another origin for the link tag? So the best way to see that is by looking at an example like this, where we have a sphere as the parent link, and then a blue box, which I'm calling leg, as the child link. And we want that box to rotate around the sphere where the two are touching. And so there's a number of different ways you can do this. You can do it just by specifying the joint origin as we were doing before. And the way you would do that is put in a Y and Z offset of 0.5 meters each, and it'll be drawn up there. And if it doesn't move, it'll actually look correct. However, if you actually start to rotate it, the child link is going to rotate around the y-axis of its origin frame. And so when we rotate it, it actually looks like this. And that's not what we want. So in order to get it to rotate properly, we want to put the joint origin down where it's going to rotate about. And so you can see we specified that with just the Y offset. And then we create another reference frame 0.5 meters up from that for the link origin frame. And that's where it's going to draw the origin of the box, which is the center. And so now when we rotate this, it'll actually rotate as we expect it to around that axis. You could also theoretically specify it with just the visual origin using the same 2.5 meters. And this will put both of the origins for the links at the center of the sphere. And this is not what you want, because this will create problems for any reference frames you create down the line. And while this model will actually rotate around the correct axis, if you were trying to rotate around any other axis, it wouldn't work. So in general, you should specify both a joint origin and a link origin to get things drawn correctly and moving correctly. So if we take a look at the example we have for Lewis, we've created a lot more links. I've created this with just the simple shapes that I talked about before. And we have the different colors. And using Robot State Publisher, we publish a transform for each one of the links. An important debugging note, if you don't specify a transform for every link, the visual elements in RViz will appear at the origin of all of your reference frames and therefore not have the structure that you want, even if it's just fixed links. So you need to specify TF frames for each one of those. And so this is the visualization that we have for Lewis. Some other things that you might want to put into your URDF files are information about collision detection. So on the top, we have the base, the visual element for this link specified as the mesh for the base of the PR2. And this is a very detailed mesh, has a lot of different facets and coloring. And if you want to do collision detection with this, it would actually take a bit of time just because of all the different parts. And so what URDF allows you to do is specify another element, another geometry for the collision detection. And so on the bottom right, you can see there a simpler mesh that is used for collision detection and has many fewer facets and therefore is a lot easier to compute collision detection for. Again, more information on this wiki page. Also, Jon and Sachin will be talking about this next a little bit in the motion planning session. There are also a lot of physical properties to your robot that you would want to describe, both for the links and the joints. For the links, you would want to specify some information about its inertial properties, which we do with the inertial tag. You can specify a mass. You can specify another origin tag, which refers to the center of gravity of your link. And then the inertia, the moment of inertia is specified by the matrix shown here. And since this matrix is symmetrical, you only have to specify 6 of the numbers, as I do here. And then for the joints, there are also a number of physical properties that you would want to model. We've already talked about the hard lower and upper limits for revolute joints. But we can also specify soft limits, which we want the controllers to operate in and not actually go to the hard limits, and we do that with the safety controller tag. We can also specify some information about the dynamics of the joint, and you can also put in the calibration information here. Another note, there are some required attributes for some of these tags, which you may not actually need. For instance, if you're just specifying the kinematics of a revolute joint, you would think that you'd only have to specify the upper and lower bounds, but you actually have to specify the effort and velocity. The units are on the wiki page. For most of my models, I just put in default values. And then there's a number of other tags that are used by Gazebo, and these are or at least documented as PR2 specific and supported for using specifically in Gazebo. And so you have things like the transmission, which describes the motor that's actually used to actuate the joints, with links to the actual package that is used to run that, and other information about that actuation. And then there are other Gazebo-specific properties that will be used, an example of which I show here, so whether or not you want gravity to affect this link, and what the coefficients of friction are, and things like that. Again, another plug for a talk. There'll be a lot more information about Gazebo and the properties of the models that you use in there later today, 2:45 by John Su and Nate Koenig. And so that wraps up the types of things that you can see in a URDF file and that you might want to create yourself. It's most of the things. There's still a couple other elements that you might see in there, and we'll talk about those in a few minutes. But first, I want to talk about some of the tools that you can use with URDF. So there's 2 different APIs. There's the main API, which is in C++. It was recently split into URDF parser and URDF interface. And Robot State Publisher is written using that. And then in the URDF parser package, there are 2 helpful scripts. Check URDF does a parse of your URDF file to make sure there are no problems without loading it into the parameter server. And then URDF to GraphViz creates a visualization of the tree structure that you create in your URDF file, as you can see part of the tree for the PR2 on the right here. And then there's also a Python API being developed partially by myself and also by Kelsey Hawkins and Thomas Moulard. Are you guys here? Okay. Well, they're helping too. My version is called URDF Python, and it's used to implement Joint State Publisher and some other tools. There are a number of different conversion tools out there. As I mentioned before, there's Collada, and there's a package for converting between Collada and URDF out there. There's also IVCon, which is used for translating different kinds of meshes. So the meshes don't have to be Collada. They can also be a number of other types. STL is pretty common. And then there's also a program that I wrote as an internship a couple years ago called Sim Mechanics to URDF. And that uses the Sim Mechanics plugin to different CAD programs like Pro Engineer to take the geometry of a model that you've built in there and export it to a URDF file with a little bit of work. And then so on the bottom right there is a model made using this tool by one of the members of the user group. But the biggest tool that is out there for helping you improve your URDF files is Zacro. And so just a couple statistics. If you were to actually write out the full URDF for a number of different models, it can get quite big. The Erratic, the Create, the Now, and the B21 Lewis all have around about 500 lines in them. But then it starts to get a bit bigger. The Carobot, Rosie, and the PR2 are all a bit bigger, with the PR2 having over 3,000 lines of code if you actually write the whole thing out. This means two things. First of all, these files get very hard to edit. A lot of the geometry is interdependent, and if you want to change one dimension of your robot, you'll actually have to change that number in a number of different places. Second, there's also a lot of redundancy. The PR2's arms are almost exactly the same with some minor changes. And so if you were to write out the entire thing, you would have to input it in twice. And so Zacro is a macro tool that allows you to get around a lot of those problems. It's used very similar to URDF. So the top is the launch file line that you would use to load a URDF file into the parameter server. And the bottom is how you do it to load a Zacro URDF into the parameter server. So instead of loading the contents of a text file, you run that command using the Zacro script, and then use your Zacro file, and that will include in all of the different, it'll run the Zacro script on that file, and then put the output of that into the parameter server. And so Zacro has a number of useful tools. You can include entire other files. You can also define properties. So here I have a cylinder that I've given the properties width and length. And I specify the parameters that I want at the top with the Zacro property tag. And then when I actually define the cylinder, for the visual element, I use the width divided by 2 for the radius. So you can do simple math on these. And then the length is the body length. And then I can use those same values for the collision geometry. And then one of the other great things you can do is use those same numbers for specifying your joints. So when I want to specify where the box should be attached, I specify it to have the origin body length divided by 2 up. And what that does is it allows me to, if I want to just change the length, I can change that parameter, and the entire model will still reflect that change that I've made. The most powerful part of Zacro is the ability to write full macros. So here I have a macro for the part that I'm calling leg, and it takes 2 parameters, prefix and reflect. And so if you look down at the bottom, I use that macro twice using the new command Zacro leg, and I use the prefix right and left, and the reflect parameter 1 and -1. And so then it just does simple substitution for the link name, so it becomes either right leg or left leg. And then the origin tag I can specify using that reflect parameter and simple math to either be on the right side or the left side, depending on what the reflect parameter is. And so using these features of Zacro, you can create a lot of smaller and more easily maintainable URDF files. So now I want to get into a couple of the different limitations that there are for URDF. So this is a common structure that you'll see called a 4-bar linkage. They can happen in a number of different parameters here. And so what you see is there's the red bar connected to the blue and the green bar, and both the blue and the green bar are connected to the yellow bar. And this creates a graph structure with a loop in it. In reality, if you just actuate one of these angles, say the blue and red angle, all of the rest will move accordingly. However, there is no easy way to represent this in URDF because, as I mentioned at the top, each link has exactly one parent. So the yellow link can't have parents in both the blue and the green links. And therefore, if we just actuate one of the joints, you get something like this, where all the other links don't move in accordance with the one link. There are ways to get around this. One way of doing it is by actuating all of the virtual motors individually using the values from the other ones. You can do this also using joint state publisher using the mimic tag. However, the mimic tag, which has been referenced in a lot of places, I think is actually only officially supported by the joint state publisher node. So you have to use a bit of hackery if you have this kind of structure in your robot. Other things that are difficult to model, as I mentioned, the 4-bar linkage. Functional gears also have a bit of the graph problem where both of the gears are attached to some solid object, but they're also touching each other and interacting with each other. You have to do, again, hacking to get those two appear to be working correctly. There's also things like pulleys, again, the same sort of dependency issues, but with the added problem of the fact that a rope is a flexible material, and there's no good way to model flexible materials except as a bunch of smaller, inflexible links. And so that makes the ropes difficult. It also makes modeling flexible things such as huggable robots or people or whatever a lot more difficult. There are also certain types of joints that you have to do a little bit of extra work to represent. Shoulders have 3 degrees of angular freedom. And if you want to represent that, the most common way to do that is by using 3 single degree of freedom joints and little placeholder links in between them, which works and is used in a lot of places, but isn't exactly an elegant solution to that. And then also just one other note that unoptimized complex models often will have a problem. At that internship where I was making the CAD models, I tried to make a URDF with a couple thousand different links, and the Willow Garage guys just laughed at me for trying to push that many transforms through TF. So you have to do a certain bit of optimization there to get it to actually work. And then one of the other big limitations of URDF is where this information actually is. So the core of URDF has information that we've talked about, the topography, the geometry, the visual information, and the joint types. And that information primarily just resides in the URDF. However, there's a number of other places where this information can be. There's the PR2 only specific tags, which still haven't gained official release status and are only used on the PR2. And so that's all the things that go into Gazebo, different sensor information, the actuation, the code that you use to run these joints. Those exist only in the PR2 specific tags. Then there's information like the physical properties, the inertial and friction coefficients. Those are specified in both the URDF and some of the specific Gazebo tags. And then information about the color of links is specified both in URDF and the Gazebo tags as well. And then you can also have information that, depending on what version you're using, is either located in individual YAML configuration files or in electric and more recent releases in SRDF, which is the semantic robot description format. And so that has information about the hierarchy, the different defining different parts. This is an arm. This is a end effector type things, information about kinematic chains, and other semantic information. And then there's also a bit of collision information that's either specified in YAML or SRDF. And so that's what elements should you check to see whether or not they collide. That information's in the SRDF or config files, whereas the actual collision geometries are defined in the URDF. And then there's other information like the parameterization that is only specified in the Zacro files. And then there's also modular pieces, which there isn't a really good way to represent here. So if you want to bolt a connect onto the top of your robot, you actually have to compile a new URDF for it to be considered functionally a part of it. There's no way to easily add these parts together or even to create a actual hierarchy of separate models. You have to just make one giant file. So the U in URDF actually stands for unified. However, there are numerous places where this information can be. However, despite these limitations, there are URDFs, as you've probably seen in this talk, are used in a number of different key systems to ROS. And so having a functional URDF of the robot that you're using will allow you to avoid all sorts of hard coding of different geometries and connectivities into specific nodes and instead put it in this common resource that can be used across many different systems. So that's what I've got. My contact information is there. You can also get all of the URDFs and some of the launch files used in this talk at the WashU repository, and there's a hyperlink for it there. And these slides will also be posted in the future. And with that, I will gladly take questions. Thank you very much. Effort. What is effort? I don't know. There are the actual units of that are on the specification online. It's a physical property that if I had paid more attention to in physics, that I would be able to answer that. Oh wait, I think Sachin has an answer. Either force or torque, depending on what kind of joint it is. That's the lovely thing about having other people in the room who know what I'm talking about. Yes? The question is there something like Zacro for launch files? I believe, so Zacro is written in a way that you can use it in general for any sort of XML. Somebody else said yes. I think it's just using Zacro, or I don't know who's. You can use the Zacro script to create any sort of XML file. So none of it is actually URDF specific. So the answer is yes. I don't know anybody who's doing it yet, but you could be that person. Yes? So clarifying on Zacro, that's pre-processed data with URDF. Yes, that's pre-processed. And so you don't gain any actual performance upgrades when you actually use it in your code, because what's actually loaded into the parameter server is the full URDF that's outputted from that. So it is pre-processed.
You're creating a URDF for a robot that you don't have detailed specs for. Let's say you have mass, dimensions, and that's about it. Any suggestions on how to go into more detailed specs like the moment of inertia and all that?
The question is, how do you if you have a robot where you have certain physical properties defined, how do you define the other physical properties like moment of inertia? I don't have a good answer for that. Maybe it'll be touched on in the gazebo talk, I'm not sure. But you can either get it from sort of other modeling software, such as the CAD programs, but I don't know how you would actually calculate the moment of inertia. Yes? The question was on the differences between VRML, right, and URDF. And I don't know VRML, so I don't have that much of an answer to that. URDF, I believe, is a proprietary format, not proprietary, a format made specifically for ROS, is that correct? So it's sort of designed for the specific use cases of creating these TF trees and that sort of thing. And I believe there are ways to interconvert between them, but I don't know as much about VRML to answer that question specifically. Yeah. The question is if there's any work for editing URDF files. Blender plugins. Yeah, I believe there's a number of different efforts out there. SimMechanics to URDF was my one sort of plugin tool. I think somebody is doing an internship on writing a converter for what is it? For different CAD models. I think there are some people working on that. Just in my own work, I've tried to create a couple scripts myself, but I don't know how much of a concerted effort there is from the top down. The question is there a way to convert from URDF to sim mechanics? At the moment, no. The sim mechanics models have a bit more information than the URDF, and part of the process of writing that script was condensing it down to the relevant information, but there's currently no conversion in the other direction. That's not to say that the open source community can't support ways to do that if there is a need for that, but currently there isn't one. Sorry? Yes, there is URDF to Collada, and Collada is a bit more of a standard that other programs can sometimes use. Is it what? Yes. So the question was, is this URDF model an input to Gazebo? Yes, it is. Using those Gazebo tags and the simulation parameters, it's loaded into Gazebo, as we'll hear a little bit more about later today. Mm-hmm. Yeah, so the question was on using simplified geometry for the collision elements. And yes, you can use any sort of simpler geometry. So you mentioned just using a bounding box. That is completely acceptable in that you can just specify a box element as opposed to the full mesh, and that'll be an order quicker. Last I checked, there were still some bugs in the collision detection so that cylinders didn't work, but I'll have to double check that.
David, take the mic, keep answering questions.
Okay.
Set up behind you. A minute or two, go as fast as you can, keep it out. Are there tools to help you make the textures? I've tried, and just end up mapped for these.
Not that I know of. There might be, but I haven't figured out that black magic myself. Oh, sorry, the question was, are there tools to help you map the textures onto the various geometries? And not to my knowledge, there might be, but somebody with more knowledge of 3D geometry would have to answer that. Not on the wiki page currently. I've been trying to figure that out, and when I do figure it out, I will update it, or perhaps you can. The biggest way, as I mentioned, is using the macro technology. That will help reduce a lot of the complexity. Other than that, it's just a bit of clever writing and being able to represent your robot in an efficient way. There are various ways to merge meshes together using tools that are out there, but really this is not aimed to be an efficient sort of representation, more a complete representation. The question was whether you can change the URDF dynamically if, say, you either attach something or there's damage to your robot, like you mentioned. Currently, you could reload the URDF parameter into your model, into the parameter server, but then you'd have to make some functionality for whatever uses that model to reload the model. So currently, I don't believe there's any particularly good way to do that. So yeah, as Jan said, there are ways to do that with to attach objects with planning.
Okay, we're out of time now. Thank you very much.
That's the answer to that question.